Okay, a quick 5-slide explanation of inferential statistics, told through 2 time-travelling examples. So, remember, research is all about hypothesis testing in experiments and correlations in particular. You have your null, there will be no significant difference or correlation, and any difference or correlation will be due to chance. Or you have your alternate, there will be a significant difference or there will be a significant correlation, i.e. it's not going to be due to chance. There was a significant difference. Chance, by the way, means luck. So there'll be no significant difference, and if you find a difference, it's just due to luck, or there will be a significant difference and it wasn't due to luck that we found that difference. Okay, so at the end of a piece of research, you want to accept one of them and reject the other, whichever way round it is. What is the p-value? The p-value is the probability that the findings are due to chance. So what is the probability, essentially, that the null is right? And it's not because of the experimental manipulation or in a correlation, not because of the two variables. Okay, so the probability that the null is correct. P equals 0.05 doesn't look good for the null. If you're saying there is only a 5% chance that the results were due to chance, were due to luck, then you're saying essentially that you've got a 95% surety that it was down to the experimental manipulation or the correlation. So that's what we get a p-value at the end of a piece of research when we run our stats analysis, and if it's less than 5%, in psychology we say we accept the alternate and we reject the null. So how does that work? Don't ask me why it's 5%, it's just regarded as that. 1970s example for you, and a millennial example for you. 2 pieces of research. In the 70s, people liked fashion and haircuts and things, as the millennials do, as you can see in that photo, them all taking selfies. So, 2 pieces of research investigating essentially the same thing. There will be no significant difference in perceived attractiveness following a haircut compared to before a haircut. Okay, so let's say people are going to rate people on attractiveness out of 50. For the millennials, there will be no significant difference in perceived attractiveness after posting an extra 100 selfies compared to before posting them. Okay, so essentially doing the same thing, and we're going to pretend that the researchers in the 70s and the researchers now did find the same data. So the data calculated is here. Let's say this was a much bigger table, but before having the haircut or before posting the selfies and after, and we've got our attractiveness ratings from our participants here. So how did they have to do it back in the 70s? Well, you had to use a bunch of formula. Okay, so in the 70s you had to apply all this data, you had to work it out with all of this formula, and you'd be looking for a value, such as a Z value or a W or a U value, doesn't matter. It's called a calculated value, because you're calculating it. It's also known as the observed value, because it's what you observed in the research. For the millennials, it's a little bit easier for them. You whack it into a stats package, okay? Or you can even do them online now. You just pop the data into the stats, into an appropriate stats test, and you click Go. So, what's the data output? For the millennials, it's easy. It tells you the exact p-value. In other words, the exact percentage chance that the results were due to chance, due to luck. So for this piece of research, p equals 0.0425 is 4.25% chance of error, okay, or 0.42% chance that the null is right. So the null isn't doing so well there. The null is going to be rejected. Let's say the same thing was found, it would be if it was the same data, by calculating the formula, but it was a bit more long-winded in the past. What we had to do was calculate it from the stats. Let's say we calculated a calculated value of 35. That's from all of those clever formula. We got 35. P is equal to or less than 0.05 critical values table. We then had to go to a critical values table that looks something like that, and you'd find them in the back of textbooks, and researchers would have these stats books on their shelves. The critical value is there was these different tables for different levels of significance. So this is for P is equal to or less than 0.05. And you find your critical value by going along the top here for your number of participants in one group, your number of participants in the other group down this side, and where the two met in the middle, you would find your critical value. Okay, so in this case, let's pretend the critical value was 23. For different stats tests, there's different rules. In the 70s, you would then go, right, 35 is higher than the critical value of 23, and therefore we either do accept our alternate or we reject, we accept our null or we reject our null. And there's different rules for the different stats test. Spearman's rho and the chi-square, the observed needs to be higher than the critical value. For all the other ones, the observed needs to be lower for it to be significant, to accept your alternate. Okay, so in terms of the exam, you just need to learn which stats test go with which independent measures, repeated measures, and the type of data, or the level of data, and you need to know whether this needs to be higher or lower than the critical value. Okay. The result for both of these results were found to be significant at a P is equal to or less than 0.05 level. And this is why we traditionally express it as P is equal to or less than 0.05. Because back in the 70s, you didn't know the exact P value. You just compared it to the P is less than 0.05 table. And you might compare it later to a P is equal to or less than 0.01 table. So you'd say it's even more significant, P is equal to or less than 0.01. But it was quite time consuming to find an actual p-value back in the day, but now the stats will tell us exactly what the p-value equals rather than is less than. As long as it was less than 5%, this means there's less than 5% chance that the results are due to chance. Therefore, the null is rejected and the alternate is accepted. Okay, and that's what the p-value is. It means there is in this case, a 4.25% chance that you have made what's called a type 1 error, which means saying that it was significant and it wasn't. But it's a very small chance, so you would accept your alternate hypothesis.